the examples that we looked at so far were based on the fact that two nodes are sharing some neighbors, right? If we follow this idea, this means that if two nodes are more than 2 hops away, if they're 3 hops away, right, then their similarity will be 0. In any scenario, it doesn't matter how similar they are, based off of all these relations, it's gonna be 0. But it won't really make sense if we say that only nodes that share neighbors, they are similar to each other, if no one else can be similar. And we looked at this idea in our, I think, second session, where we were discussing the regular equivalence between two nodes. So regular equivalence is saying that two nodes, you see here, for example, we had an example of CEOs in a company where these guys are basically at the top were CEOs, these were over here by board members, and these were basically just some staff. Same for the other company, but they were not directly related to each other because they were two other companies. So, but they're still similar. This guy is CEO, this guy is CEO. So we should find a measure of similarity that shows that, right? So the idea with regular similarity is that two nodes are similar to each other if node, let's say Vi, has a neighbor Vk, and Vj, node Vj has a neighbor Vl, and these neighbors Vk and Vl are similar to each other, right? So Vi is similar to Vj if Vk is similar to Vl. That's the idea with all global overlap measures. So let's write that relation in index notation. We have this relationship here. So you can see that this AIK is the adjacency matrix, and it's the element that shows if node I is a neighbor of node K, right? And this guy, JL, is showing if node J is a neighbor of node L. So if both of these are 1, it means that Vi has a neighbor called Vk, and Vj has a neighbor called Vl. And then we call our measure of similarity S between nodes K and L. So if basically if nodes Vk and Vl are similar to each other, then there would be a similarity here between nodes Vi and Vj. If I is not connected to K, or J is not connected to L, or they're connected, but they're similar, but those two neighboring nodes have no similarity, then this will show no similarity. So that's the idea in index notation, mathematically speaking. But there are two problems with this. One problem is that this won't show self-similarity necessarily in all the cases. So here you can see this equation, basically this shape here. We have a node Vi that has neighbor Vk and neighbor Vl. So a node, by any measure, we're expecting it to be similar to itself, right? We won't, it doesn't make sense if a measure of similarity says that a node is not similar to itself. So here you can see that Vi has neighbor Vk, Vi has neighbor Vl. So based off of this idea, if Vk is similar to Vl, Vi is similar to Vi. You write it here, Sii, and then over here, Aik, fine, Ail, again, fine, both of them are connected to, both Vk and Vl are connected to Vi, so these are 1, but SKL, here see, these two are not connected to each other, so based off of this measure, these are not going to basically, this guy is not similar, which doesn't make sense. Another issue that stems again from self-similarity issue is that if two nodes Vi and Vj share a lot of neighbors, we expect that, based off of the old local overlap similarity measures that we discussed earlier, they be similar to each other, right? be similar to each other, right? So, but that doesn't necessarily hold, and we will see why. Over here we have Vj and Vi that have 3 neighbors in common, and they have 2 other neighbors that don't share, right? And but they are connected to each other. So when we write our basically similarity measure equation here in mathematical notation, we can divide this sum. So we have 2 sums over all the nodes Vk and over all the nodes Vl that are neighbors of J and Vks that were neighbors of Vi. So we can write Vl as in 2 parts. We can say Vls that are not Vks, so they are not overlapping Vk and Vl, and the ones that are overlapping. So we go over all nodes, 2 sums. Sometimes these might overlap. So if we look at the ones that are overlapping here, we see that Vk, has 2 neighbors, Vj and Vi, that are not connected to each other. So based off of this, skk, again, as one that we saw before, skk, it's not self-similar. So the neighbors of Vi and Vj are not similar to each other because the node is not similar to each other, right? To itself. And there is no contribution coming from these 3 nodes. And we have some contribution from this node. But the fact that these 2 nodes are sharing a lot of neighbors won't account to anything in this scenario. So these 2 issues need to be addressed. And we can address that by adding there's basically Dirac Kronecker delta. So yeah, the Kronecker delta at the end, and this equation will show self-similarity because delta ij is equal to 1 when I is equal to j, and it's equal to 0 when I is not equal to j. Therefore, that's what's going to happen. So we write that again in matrix notation, and this is what we have. So we have this, and we try to solve this iteratively. We start from some s, 0, some matrix s equal to 0, all the elements equal to 0. And then we iteratively solve it like this. And we see that, okay, let's plug 0 into this. It's going to be I, right? Then I plug I into this equation again, I will get a squared plus I. And then I plug this again, I will get a to the 4th plus a squared plus I. And so on and so forth. So the pattern, the pattern is obvious, right? So we are just summing over the even powers of the adjacency matrix. And we are continue that until forever. So what that means is that based off of what we learned in the first session, that the power k of the adjacency matrix shows the basically number of paths of length k between those 2 nodes. This means that for finding the similarity between 2 nodes, I'm looking at how many paths of even length are basically connecting these 2 nodes, right? So if there's a lot of paths of even length that connect 2 nodes, it means that they're too similar. But why just even? That doesn't make any sense. So if 2 paths have 2 nodes have too many paths of odd length, then they're not similar, right? So that idea doesn't really make sense. And we need to reformulate our original idea based off of that. So here how we reformulate our problem. We said that at first, we said that we have a node Vi that has a neighbor Vk. If that is similar to node Vj's neighbor Vl, then those 2 nodes Vi and Vj are similar. We reformulate that by excluding the neighbor of Vj. So we say that if node Vi has a neighbor named Vk, and if that is similar to Vj, then nodes Vi and Vj are similar to each other. So if Vi has a neighbor Vk, similar to Vj, that means that Vi and Vj are similar to each other. We write that in index notation, and we see that one of the adjacency matrices that we had here is gone. Okay, we write that in matrix notation, and this is our matrix notation. So again, we can start solving this iteratively. We start from a 0, right? S equal to 0, we plug that in, we continue. It's gonna be just, different powers of matrix A, 4, 3, 2, 1, plus I. So not just the odd, basically, powers, even powers. So we write that, and this is gonna give us this relationship. So this relationship is a geometric series of matrices. Let's look at the solution and see when it's true. So we have, let's represent that geometric series of matrices as Sn, and then we multiply both sides by x. We can, on right-hand side, take this into our summation. We multiply each element of the sum, so it's gonna be from 1 to n plus 1. So we can take that as basically out of the summation, right? Not factor it, just take it out. It's gonna be x n plus 1 plus this summation. So the difference is that we are lacking an I here, right? You're lacking an I. So we can add that I back. We take this to the left-hand side, right? We add I with negative sign this time. So we can write this now as Sn, right? We missed basically I equals 0. We added that on both sides. We can write it as Sn. We can factor Sn out. This is the relationship we are left with. And we just divide the right-hand side by x minus I. And that's going to give us a solution to our problem. So now we want to see what's the solution for this when n goes to infinity. If the largest eigenvalue of our adjacency matrix is less than 1, then not adjacency matrix of our basically matrix X is less than 1, then the solution for this is gonna be 0, and basically this is gonna be I minus X inverse, right? So we have a term, the alpha term, that is multiplied by the adjacency matrix. We need to ensure that it is chosen so that the largest eigenvalue of our matrix A, basically our matrix alpha A, is less than 1. So this is called Katz similarity measure. And using the solution from our previous slide, we can write this as I minus alpha A to inverse, right? Okay, so there is a problem with this relation. And the problem is that if we have nodes of higher degree, right, it generally speaking means that these nodes have a lot of paths of different length coming to them, right? So compare, for example, remember the Florentine family's graph. We had some nodes that were on the corners, they only had one neighbors, but we had some nodes that were more central. We had some nodes that were more central. So the ones that were on corner, they had lower degree, and there were lower paths essentially ending to them of different size. So the ones that have higher degree in general have higher number of paths ending at them. For that reason, this Katz similarity, which is based off of the idea of number of paths ending at that node, will be biased against the ones that have lower degree. And we need to somehow find a relationship that takes care of that, to essentially make sure that we are not biased toward that. So the first idea that comes to mind is some sort of regularization, right? We want to normalize the Katz similarity measure so that our basically output, our similarity measure is not geared towards the ones that have higher degree. For this, we have the idea that if a node is participating in more paths than what we expect them to participate in, then we will give them higher essentially similarity score. But if they are not, if they are, participating in as much paths that we were expecting, then they won't get as much higher. So we kind of want to normalize this measure by the total number of expected paths that go through this, right? So here is how that will look like. So this is called LHN, measure of similarity. It is named after essentially 3 people who wrote a paper on this. I just know N, which is Newman, if I'm not mistaken. Which is author of one of our books, our textbooks. So based off of that, we have the same relation as Katz similarity, but we are dividing this term, the different powers of the JCC matrix, over the expected value, basically expectation of different powers of the JCC matrix. So for that, we use something called a configuration model. In configuration model, what we have, so let's say that we have this graph that have a set of nodes, and it has a set of edges. So we have node V1, we have V2, V3, V4. Each of these have a degree, right? So this guy has degree 1, this guy has degree 3, these guys have degree 2, right? Each of them. Okay, so a configuration model essentially keeps the degree of the nodes, but wipes all the edges between these. So we have a set of nodes, and we have a set of degrees, corresponding degrees for these nodes. Now in configuration model, we basically draw all the edges just randomly, just given these basically degrees that we have. So let's say that, for example, I can draw this graph, which has V1, again, has degree 1. V4 has degree 2, sure. We have V3 that has degree 2, sure. And V2, there's a self-loop here this time. So it has a degree 3, sure. So this is basically a different graph, but it has the same nodes and it has the same degrees. Again, same for here. We don't have self-loop, but we have 2 edges between V2 and 3, such that V1 again has degree 1, V4 has degree 2, V3 has degree 2, and V2 has a degree 3. So we essentially use a configuration model. We wipe all the edges, and using that, we look at how many edges we are expecting to have between 2 nodes. And for basically finding that will give us our expected number of paths between 2 nodes. So let's look at this. So we are saying that what is the expected value of length 1 paths between node Vi and Vj? We have a node Vi. The only thing we are left with is its degree Di. We have a node Vj, and the only thing that we are left with is its degree Dj. Now, in total, so if the degrees are intact, we will have the same number of edges. So look here, we had 1, 2, 3, and 4 edges here, right? We have 1, 2, 3, and 4 edges here, 1, 2, 3, and 4 edges here. So the number of edges is still in this model is gonna stay same. We have, so let's call the set of degrees, set of all the nodes that, set of all the edges that we have E, and we call the number of them with E, essentially absolute value of E, but modulus of E, but I'm just saying E. So we have E edges. Each edge is connecting 2 nodes. So there are a total of 2 E endpoints that are participating in basically this graph. And then out of these 2E nodes, DJ nodes are DJ basically connections. DJ ends of the adjacency matrix are connected to node Vj, right? So the basically if so the probability out of basically 2E endpoints of edges, DJ of them are connected to node Vj. And possible probability of any edge coming to this is gonna be DJ over 2E. And then I have DI that are coming from this. So there's a probability of DI times DJ over 2E that there's an edge basically connecting nodes VI and VJ. We continue that for the basically case of two nodes, let's say, I'm sorry, the paths of length 2. So for that, I have 3 nodes, right? I need from node I go to an intermediate node, VK. And then I jump from node VK to the endpoint VJ. So we say that what's the probability, what's basically expected number of edges from VI to VK? It's 2 nodes, right? I can use the same relationship that we drew up there, right, up in the slide. So so DI, the degree of node VI times the degree of node VK divided by 2E, which is the total number of edges between these two. Then I have the same thing here, right? But so node VK had DK edge, basically degrees, DK edges connecting to it. And one of them has been used because I connected VI to VK. So I'm gonna say DK minus 1 times DJ over 2E. Now you might say that, okay, you also use one of the edges when you moved from VI to VK, right? So this is gonna be 2E minus 1. But in reality, in practice, DK is usually, orders of magnitude smaller than the total number of edges in our graph, the node, basically degree of the node. So subtracting 1 from this doesn't really make any differences. And that's how basically in practice people use this relation. Go ahead.
Can you clarify what is the absolute value?
So I'm writing G, notation for G is basically graph. A graph is defined as a set of nodes and edges, right? So let's say that set of nodes, for example, for a graph is V1, V2, and V3. Let me move to chalkboard. Okay, so it's basically like this. And then let's say some of these, let me actually draw this. So let's say that this is a graph. We have V1, V2, and V3, right? So this is how I show the set of nodes in our graph. And I show the set of edges in our graph. So edges are pairwise nodes, right? So there's 2 ways to write them. So one way is just write them as the pair of nodes, V1, V2. Then I have V2, V3. Then I have V1, V3. And another way to write it is just by writing, representing that with epsilon. So epsilon, they say that epsilon 1, then V2, V3, epsilon 2, V3, V1, epsilon 3. So we said, so this is the set of nodes, and this is the set of edges, and this is a basically simple graph. And we say that the total number of edges, we represent that with the size of set E, and the total number of nodes in our graph is represented with size of set V. So we found basically the expected number of edges from VI to VJ, where the intermediate point was VK, but so two ends are, we know which two ends we are talking about, but the intermediate point can be any node essentially, any node VK. So we need to sum this over all the nodes VK in our graph. So any paths of length to from VI to any node, and then from that node to VJ. So we have two essentially values that are a function of basically K. That's degree of node K. So we take everything out, we are left with Dij over 2e squared. And inside that summation, we are only left with dk times dk minus 1. And that's going to be the relation for that. So, okay, so if I want to continue this for all the sizes, it's not going to be possible. As E grows larger and larger and larger, it can, technically speaking, go to infinity. So we'll come back to see what basically we need to do to find essentially, I said, okay. So yeah, sorry. So basically we'll come back to see how to solve this.